Section 4.6, Linear Approximations and Differentials. In this section, we will be using many of the techniques that we've already used in previous sections, and we're just adding some more vocabulary to what we've already done. And so hopefully you won't find the techniques that we do in this section to be much different than what we've done in the past, just some new vocabulary to go along with that. And the first thing that we're going to look at is a linear approximation. And oftentimes in applications, people will want to use a linear function in applications instead of maybe something that's a little bit more complicated, because it will cut down on the computation time. It may be that a linear approximation provides a good enough approximation for whatever the application is. And so this is used in a lot of times in physics. They'll use linear approximations to go ahead and perform computations. So let's look at this function that we have here on Desmos. This is the function, let's see, it's coming up, y equals x cubed minus 2x squared plus 1. And so let's say we're interested in at x equals -1, I think the value of the function is -2. And let's say we're interested in doing a linear approximation at that point. So basically what that means is we're going to find the tangent line at that point. A linear approximation is assuming, so let's do this. Let's put that point in there so you can see it. So that's the point -1 comma f of -1, which I believe is -2. And, let's call this f of x. There we go. All right, and so that point right there is the point -1, get right on top of it, -1, -2. And a linear approximation is saying that if I zoom in on that point and I keep zooming, keep zooming, keep zooming, and I got really close to that point, essentially that becomes a straight line. All right, and we can use a line to approximate the function near that point. And so basically what we're doing is we're finding the equation of the tangent line at that point. We've done that calculation many times. So to be able to find the equation of the tangent line, we need to find the slope, which is going to be the derivative evaluated at x equals -1. And we need this point, -1, and in this case it's -1, -2, and we're going to write the equation of that tangent line. So over here on the side, we're doing that same calculation that we've done in the past. I took the derivative, I got 3x squared minus 4x. I evaluated it at -1. When I evaluated it at -1, I got 7. So the slope of that line is going to be 7, the slope of the tangent line. I also evaluate the point, or evaluate the function at that -1 to find the point. And so when I put in -1 into the function, I get -2. And so I know that the point -1, -2 is on that graph. Now I'm going to use this information that I know the slope and I know the point to write the equation of the tangent line. And so we've done this many times. We say y minus the y value of the point, y minus -2 is y plus 2, equals the slope times x minus the x value of the point. And so we get this as our linear approximation. We can simplify this, subtract 2, and then distribute the 7, and we will end up with y equals 7x plus 5. So if I type in y equals 7x plus 5, that's the equation of the tangent line at that point. And as you can see, since we're zoomed in so far, that blue tangent line is almost exactly on top of the function. And so we can use this to approximate the function near that point. And this linear function is less complicated, and so it would, if you were doing multiple computations, it would save you time and computing power to use a linear function instead of this cubic function. And so let's say I wanted to approximate maybe, what did I say? Oh, let's go back. What your book is going to call this linear approximation is it's going to call it L of x. So I will find the equation of the tangent line, and then I will switch to this notation that your book is using, calling that the linear approximation. They call it L of x. It's just saying the equation of that tangent line. And so if, let's say I wanted to use this approximation to approximate the function at x equals negative 0.9. So I could put negative 0.9 into my linear approximation, put in negative 0.9. If I do the arithmetic that goes along with that, I get negative 1.3. Right? So that is the approximation to the function at negative 0.9. Now let's just see what it would actually be, the exact value that we would get if we put in negative 0.9. If we typed in, I can type that into here, I can say what is f of negative 0.9? I get negative 1.349. And so you can see that these are pretty close, and depending on what you're working on, maybe they're close enough, maybe they're not close enough. It would depend on the context that you're working in. All right, but this is the linear approximation, and this is the exact value of the function at that point, or at that x value. Now, being able to do a linear approximation depends on the function being differentiable at the point that you're looking at. So let's say I look at this equation instead, and I want to know something about the absolute value of x at x equals 0. Well, if I zoom in at x equals 0 and keep zooming in, I can zoom in forever, and at x equals 0, that's never going to be a straight line. There's always that sharp point, so we can't use a linear approximation on something that's not differentiable at that point. So this is what we were just doing. All right, y minus the y value of the point. So if I go back up here, I said y minus f of a, negative 2 was f of negative 1. I could have said that was f of negative 1. Y minus f of negative 1 equals the slope, f prime of negative 1, times x minus a. Our a value was negative 1. So this is just the equation of a tangent line. The only thing from this step to this step is that they've added f of a to both sides of this equation. So basically it's this step, except for that negative 2 would be written in front. It would be negative 2 plus 7 times the quantity x plus 1. So these two things are just representing the slope, or not the slope, representing the equation of the tangent line at that point. And then they're calling this thing, this whole thing, they call the linear approximation. And so this is just notation that your book uses. You could call this y, but they call it L of x. And so in your homework, they're going to ask you what L of x is, and that's just in place of y in this equation of your tangent line. You have several problems in your homework that are like this, 25 through 36 linear approximation. It says A, write the equation of the line that represents the linear approximation to the following functions at the given point A. Use the linear approximation to estimate the given quantity. Compute the percent error in your approximation, which is 100 times the approximation minus the exact over the exact, where the exact value is given by a calculator. All right, so let's start with this f of x equals 12 minus x squared. A is equal to 2, and we're trying to approximate f of 2.1. So what we're going to do first is we're going to find the equation of the tangent line to this function at x equals 2. So just like we've done many times before, we're going to take the derivative. We're going to take that derivative and evaluate it at the a value at a equals 2. And we get the derivative is equal to negative 4. This is the slope of our tangent line. Right? We also need a point. So we need to take this 2 and put it into our function to find the actual point. So 12 minus 2 squared is 4, 12 minus 4 is 8. And so we get the point 2, 8. Now we're going to write the equation of a tangent line. Again, I use y because I'm used to that. So I say y minus the y value of the point equals the slope times x minus the x value of the point. Do some arithmetic. I added a to both sides, or in this case 8 to both sides. In the book, this 8 came first. It doesn't matter if you put it on the front or at the end. And then just do some arithmetic, -4, some algebra, distribute your -4, and then combine, and you get -4x plus 16. This is what they're going to call L of x. That's the linear approximation to the function at that x value, a is equal to 2. So then it says use the linear approximation to estimate the given quantity. So we want to know what f of 2.1 is. We want an approximation to that, so we're going to put 2.1 in for x. -4 times 2.1 plus 16 is equal to 7.6. And we just want to know how accurate that is, because we can actually use our calculator to calculate the exact value or an approximation. If it has a bunch of decimal places, it's an approximation still, but we can still calculate the percent error to some degree. So the exact, we would say f of 2.1. So if we want to know the exact, we take 2.1 and put it into the original function. So 12 minus 2.1 squared is equal to 7.59. So the linear approximation gave 7.6. The exact is 7.59. And then if you want to find the percent error, you do that by just following this calculation. We take 100. I usually multiply times 100 at the end. You take the approximation, so I'm going to take 7.6. I'm going to subtract 7.59. If that's negative, I'm going to take the absolute value of it. The percent is a positive value. The percent error is a positive value. And I'm going to divide that by the absolute value of the exact. So in this case, I took 7.6 minus 7.59 divided by the absolute value of 7.59 times 100. And that ends up giving you a percentage of 0.1318%. And depending on how the question is asked, you'll be asked to keep a certain number of decimal places, and I don't know what it is for this problem in MML. So this next problem, f of x is equal to 1 over x plus 1, and a is equal to 0. And then they want us to approximate 1 over 1.1. So they don't tell us the x value. They don't say f of an x value. They want us to approximate what this is, and we'll deal with that in a second. So same process, we're going to take the derivative, rewrote this so that it's easier to take the derivative of, use the chain rule, brought the -1 down in front, -1 times x plus 1, decrease that by 1, we get -2, multiply times the derivative of the inside, but in this case the derivative of the inside is just 1. Rewrite that, all right, without the negative exponent, we get -1 over x plus 1, the quantity squared. And we need to evaluate that at a equals 0. That's the x value that we're interested in. So f prime of 0 is -1 over 0 plus 1 squared, which is just 1. And so we get -1 over 1, which is -1. We also need to find the point. So we put 0 into the original function to find the point. When we put 0 into the original function, we get out 1. So the point is 0, 1. Now we do our linear approximation, or find the equation of our tangent line. We take y minus the y value of the point equals -1 times x minus the x value of the point. And then just do some algebra and you get y equals -x plus 1. Your book is going to call that L of x. That's fine. Now, this is where it gets a little bit weird. They want us to approximate 1 over 1.1, or 1 over something plus 1. Well, 1.1 is equal to 0.1 plus 1, and so this is telling us that x is equal to 0.1. And so we're going to take this 0.1 and put it into our linear approximation. -0.1 plus 1 is 0.9. So this is the estimation using our linear approximation. And then we calculate the percent error by finding the exact. You take the approximation minus the exact divided by the exact absolute value if needed, and then you multiply that by 100, and in this case you get about 1%. All right, let's move on. You can use concavity with your function to determine if you have an over approximation or an under approximation. So let's look at the two situations that we have here. If our function is concave up at the point that we're interested in, and then we draw our tangent line there, or our linear approximation, we can see that the actual curve is above that linear approximation. So that means that the linear approximation would be an underestimate of the actual value of f. As opposed to if we have something that is concave down, right, then we put in our equation of our tangent line, or draw our tangent line in there, or our linear approximation. And if our function's concave down, we can see that our function is going to be below the actual linear approximation, meaning that the linear approximation is an overestimate of the function. We're not going to do any examples of that, but you do have a homework problem that addresses that, and maybe a couple homework problems that address that. Another way to talk about the derivative and use it as an approximation is to, instead of finding actual function values or approximate actual function values, we may just want to know how much the function is changing. And so we use the derivative, and if you divided by delta x on both sides of this, you would get delta y over delta x is approximately equal to f prime of a. And what this is saying is that the slope is if we're exactly at a, the slope is f prime of a. But once you move off of a, move off of that x value, if I look at, let's go back out, zoom back out. All right, so let's say I'm right here at x equals -1. Well, the slope at x equals -1 is 7. All right, but the instant that I move off of -1, that slope changes. And so if we're going to use a linear approximation, we're saying that that slope is approximating for values near x equals -1, but it's an approximation because we know that once we move off of -1, that slope would change. So we say delta y is approximately equal to f prime of a times delta x. And we can do a variety of problems. You have problems in your homework that have you use that idea. So these three, we're going to do 2 of these problems. Number 55, it says approximate the change in the volume of a sphere when its radius changes from 5 feet to 5.1 feet. And they give you the formula for the volume of the sphere. So we start with v of r equals 4/3 pi r cubed. And using the context, or using the notation that was produced in the slide before, we know that delta v is approximately equal to v prime of r delta r. So delta y is equal to, in this case, y is equal to f of x. So f prime of a delta x. Rv is taking the place of y, and r is taking the place of x. And we are finding the derivative of our function v with respect to r. In your homework, I often used dv dr instead of v prime of r when I was doing this calculation. So you'll see me, I will write dv dr off to the side and calculate my derivative. In this case, my derivative is 4 pi r squared. And so I'm using this notation instead of that notation. Both of them are accurate in this case. So I just said that the derivative of this is 4 pi r squared. And so you're going to substitute 4 pi r squared in for v prime of r. And we were starting at r equals 5. So you put in r equals 5. And then the change in r, we're going from r equals 5 to 5.1. So our change in r is 0.1. So we fill in the pieces, 4 times pi times 5 squared times 0.1. And if you multiply that out, you get 10 pi, that the change in volume is approximately equal to 10 pi. And the units on this were in feet, and so units on volume are feet cubed. So that's the change in volume, an approximation of the change in volume. If you wanted the exact change in volume, you would substitute v of 5.1. You would put 5.1 in here, find that value, then put in 5, find that value, and subtract the 2. And so this is a little less complicated than that, and it's an easy approximation. So I skipped 56, went down to 57, very similar problem. In this case, we have the volume of a right circular cylinder of fixed radius r equals 20 centimeters. And then they give you the equation for the volume of a right circular cylinder, but it's just a function of h because they're fixing the radius. The radius isn't going to be changing, and so you can substitute in 20 for that r right away because it's not going to ever change in this problem. So we get this as the equation for our volume. Delta V is approximately equal to V prime of H. Oops, this could be delta H. V prime of H delta H. I calculate V prime of H, take the derivative of this with respect to H. We're just going to get 400 pi. We substitute that in to this equation. All right, so we put 400 pi in there. The change in H, now the reason I chose to do this problem is that it is decreasing in this case. It's going from 12 down to 11.9. So we need to put -1 in for, or -0.1 in for our delta H because we're going from 12 down to 11.9. So the change in volume is going to be negative in this case. -40 pi centimeters cubed because the units were centimeters and units on volume are centimeters cubed. Another way of asking a very similar question without a context is something that looks like this. Approximate the change in y equals f of x equals x to the 9th minus 2x plus 1 when x changes from 1 to 1.05. So this one we're just using that relationship directly. Delta y is approximately equal to f prime of x delta x. So we take the derivative of this function, which is 9x to the 8th minus 2 times delta x. The x value that we're starting at is 1. And then the delta x is, we're moving from 1 to 1.05, so we put in 0.05. And we just do this calculation and get 0.35. Not anything very different about that, and I'm not going to do part B of this example. The last thing that we're going to talk about in this section is this term differentials. And for our purposes, differentials are just going to be a vocabulary term that kind of represents what we've already been doing. If you move on and you get into some more technical mathematics where you are asking to do some more proofs, your treatment of differentiables needs really some more mathematical rigor to be able to talk about using these little dx's and dy's and be able to move them around algebraically. But for our purposes, we don't need to dive into that mathematical rigor, and it'll just be another form of notation that's describing what we have been doing. And so this idea of a differential is trying to describe this, instead of calling this delta y is approximately equal to f prime of x delta x, we are looking at something that looks like, and a terminology that we've already used is that dy dx is a terminology that we have used to describe a derivative. And basically what happens, which this is where the mathematical rigor part is a little bit hand-wavy, is it's like we are multiplying by dx on both sides, and we get dy equals f prime of x dx. Now really, to treat those things algebraically, we need a little bit more mathematical rigor, but for our purposes, this is okay. So this is a way of getting out of this delta y is approximately equal to f prime of x delta x, and saying, all right, we're going to call it dy, and we're going to say dy equals f prime of x dx. In general, it's just another notation that describes basically the same thing. So instead of just saying delta y is approximately equal to, delta y represents the actual change, dy is the approximation. This little dy represents the approximation to delta y. And so just to use that language with a couple of examples, I chose this number 62. It says consider the following functions and express the relationship between a small change in x and the corresponding change in y in the form dy equals f prime of x dx. The only thing that they're asking you to do here is to write out this expression. So dy equals this is f prime of x. And basically you get some practice doing some derivatives. So this is sine of x. The sine squared of x is the same thing as sine of x, the quantity squared. Bring that 2 down in front, 2 sine of x, multiply times the derivative of the inside, and we get cosine of x. So we had to use the chain rule there. And so all they're asking you to do is write out this. Number 63, similarly, gives us some practice, x to the negative 3. Take the derivative of x to the negative 3 equals negative 3x to the negative 4, or negative 3 over x to the 4th. And we're just taking this and putting it in where we see that f prime of x. And if they gave us a small change in x, we could approximate that change in y. And so your homework deals with asking you to make these approximations. Sometimes it'll give you values to put in for this and to get the actual approximations. But mostly these are things that we have done before with some new vocabulary. So again, we have section 4.6, the homework, and section 4.6 quiz. Please let me know if you have questions and have a good time with this.